at which position between a and b does x need to lie such that the combined surface of these two figures is as small as possible. That's the puzzle that we'll be solving in this video, and we'll solve this problem by using derivatives. So let's look at it in more detail. We have 2 points, a and b, and between them a straight line with a length capital L. On this straight line, we have a variable point x, and what this x does is it defines two figures. On the left-hand side, the distance between a and x is the diameter of a semicircle, and the remaining distance between x and b defines the length of an equilateral triangle, meaning that each side of this triangle will have a length of small l. Now, as I said before, this x is a variable position. It can slide across between a and b, and for each different situation we'll have different figures, but still a semicircle and an equilateral triangle. For instance, if x lies way more to a, we have a small semicircle, but a very large equilateral triangle. On the other hand, if x is much closer to b, we'll have a much larger semicircle and a much smaller triangle. Therefore, for each different position that x takes, we'll have a different surface of the semicircle and a different surface for the equilateral triangle. And therefore, for each different position of x, we have a different sum of surfaces. The total surface is simply the surface of the semicircle plus the surface of the triangle. And the question that we're asked now is for which position of x between a and b is this combined surface as small as possible? The first step is of course to realize that we're dealing with an extremum problem. We have this total surface of both figures and we need to find its extremum, in this case the minimum. Therefore, this problem is perfectly fit to be solved by using derivatives. However, derivatives are taken of functions. Therefore, in the second step, we need to find the function that describes the total surface of these two figures as a function of x. So concretely, we need to find a way to express this surface as a function of x, which boils down to finding a way to express the separate surfaces of the semicircle and the equilateral triangle as a function of x. So let's do that right now. And to do this, let's draw our initial sketch again with an x at some arbitrary position. First, we look at the surface of the semicircle. This is quite straightforward because we see that the distance that is taken as the diameter of this semicircle is simply the distance x. And because we know that the surface of a whole circle is written as pi times r squared, or pi multiplied by the diameter squared divided by 4, we find that the surface of our semicircle is equal to 1/2, because we're dealing with a semicircle, multiplied by pi, multiplied by the diameter squared, but the diameter in this case is simply x, so we have x squared divided by 4. Or written differently, we have 1/8 times pi multiplied by x squared. So we see that we're already halfway down, because we've written the surface of the semicircle as a function of x. Now we turn to the surface of the equilateral triangle. And now we turn to the surface of our triangle. And to do this, we remind ourselves that we're dealing with an equilateral triangle, meaning that this distance will be the same as this one, and it will be the same as this one. Now, we know what the length of each of these sides will be. They will simply be the entire length between a and b minus the length between a and x is a variable position. Thus, the resulting distance, which is this distance, so one side of the equilateral triangle, will simply be L minus x. Therefore, we are left with calculating the surface of an equilateral triangle by knowing the length of its sides, and let's note them here as small l. Now we know that the surface of a triangle is equal to 1/2 multiplied by the height of the triangle, which is basically this length right here, which we call h, multiplied by the base of the triangle, which in this case is simply L. Now we need to find a way to link this h with this L, because L is the only distance that we have, namely this capital L minus x, and we don't really have an expression for h. So how can we link this? Well, because we have an equilateral triangle, we know that all of these angles are 60 degrees, which means that half of this angle is 30 degrees. And therefore we see that L and h are linked to each other by the cosine of this angle. So we know that for an equilateral triangle, we have 1/2 times L times the cosine of this angle, which is 30 degrees, multiplied by L. Now we know that the cosine of 30 degrees is the square root of 3 divided by 2. So we get 1/2 multiplied by the square root of 3 divided by 2 multiplied by L squared. And this is the surface of an equilateral triangle by knowing the length of its sides. And we can now use this formula to calculate this specific surface right here, because the length of each side is capital L minus x. Therefore, the surface becomes the square root of 3 divided by 4 multiplied by the length squared. In this case, the length will be L minus this x, and we square this. And now that we've written both of our surfaces separately as a function of x, we can of course write the total surface as a function of x. This simply becomes the first surface, which is pi divided by 8 multiplied by x squared, plus the surface of our equilateral triangle, which is the square root of 3 divided by 4 multiplied by L minus x squared. And this is the function that we were looking for, because it is a function which expresses the total surface of our two figures for a specific x. So it's a function of x. And we know that if we want to find the minimum or maximum of such a function, that we need to derive it to x and then put the derivative equal to 0. And this will give us the x for which this function is either maximal or minimal. So this brings us to step 3, where we have to derive our function. So we need to derive to x the following function. Pi divided by 8 times x squared plus the square root of 3 divided by 4 multiplied by L minus x squared. Now this is very straightforward. For the first term, we simply get pi divided by 4 times x. And the second term is also straightforward, but we need to take into account the chain rule. We get the square root of 3 divided by 2 multiplied by L minus x, and we multiply this by minus 1 because we have this minus sign in front of the x. And this has to be equal to 0. Rewriting this, we get the following. We have pi divided by 4 multiplied by x minus the square root of 3 divided by 2 multiplied by L plus the square root of 3 divided by 2 multiplied by x. And for the specific x that we are looking for, this of course has to be equal to 0, because for this x, the surface of our two figures is minimal. So we are left with a very simple algebraic equation. If we take together all of the terms with x, we get pi divided by 4 plus the square root of 3 divided by 2 multiplied by x. And the remaining term we put on the other side of the equality sign, so the square root of 3 divided by 2 multiplied by L. Now to get rid of this 2 in the denominator, we multiply both sides of the equality sign by 2. This way we get the following. We get pi divided by 2 plus the square root of 3. This is the factor in front of the x. And on the right hand side, we simply get the square root of 3 times L. And this brings us, of course, to our final result. We have that the x for which our function is minimal, so the surface of our two figures, is equal to the square root of 3 divided by pi divided by 2 plus the square root of 3 multiplied by L. And to get an idea what this actually means, we can simply calculate this term in front of the L, which is the total length between A and B, and we get that x is approximately equal to 0.52 times L. This solution means for our original sketch that if x is just over halfway between A and B, that the sum of the individual surfaces of our semicircle and our equilateral triangle will be minimal. Now, before we end, there is of course one thing to address here, and a question I will leave to you guys to try to figure out. Somewhere along the way, we assumed that the 0 point of our derivative would give us the minimum surface of these two figures. However, what's to say that this doesn't give you the maximum of these two figures? Well, that's something I leave as a question to you. And if you struggle with this, leave a comment in the comment section below and I will be sure to give you the full explanation. As an added problem, you can also try to figure out how to calculate the maximum combined surface of our two figures. Where does x then need to lie? And with those questions, I thank you for watching and I will see you in the next one. Bye.